So here's an outline of what we're doing in this week. In the previous lecture, I gave you some background that will motivate, that'll help us understand why the pumping lemma works and what it means. And in this lecture, we're going to learn about the pumping lemma and do a bunch of proofs that use the pumping lemma so that we can prove that languages are not regular. So if you remember, we did a whole bunch of examples like this where we took a DFA and we said, well, look, this DFA has 5 states, which means that any string that's longer than 5 characters is going to have to visit some state at least twice. And we did this whole slicey thing to see why that's true. And given that it has to, say, go back to state 2 in this example, we can repeat this Y part, right, the stuff in between, we call it pumping, as many times as we like to give us more strings in the language. So for example, if we take 2 copies of the Y, then we get this string here, right? That's X, Y, Y, Z. And that's got to be in the language because when we got to this 2, we could do it again. And for example, if we take 4 copies of the Y, right, that's also going to be in the language of our DFA. And if we get rid of the Y altogether, right, we can also find a string that's in our language, that's in the language of the DFA. All we need to do is start with a string that's in the language that is longer than the number of states, and we can do this whole magic pumping thing. So for example, if our DFA has 10 states, then any string that's at least 10 characters long is going to have to visit at least one state twice, right? And if that string is in the language, then XYYZ is going to be in our language, and XZ and XYYZ and XYYYZ and so on, right? If it's a 10 state DFA. And if it's a 23 state DFA and we have a string in the language that's at least 23 characters long, that's going to have to visit at least one state twice, right? Some different DFA. And XYYZ, once we did the right split for that string, right? Each string has a different split, remember, because each string has to do with, the split has to do with what states we visited to process that string. But once we figure out what's the XYZ part for the string in our 23 state DFA, we can also know these things. Same if we have a 54 state DFA, right? The string split might be different, what the X is, what the Y is, and so on, but XYYZ is going to be in our language and XZ and so on, right? And of course, you've figured out the pattern by now here, right? If our DFA has M states, then any string that's in the language that has at least M characters is going to have to visit at least one state twice. So we can take any string we want. We pick a string, and if it's in the language and it's at least M characters long for a DFA with M states, then we can split it up into an X part, a Y part, and a Z part using this slicey thing, right? And that gives us a whole bunch more strings that are definitely in our language. Okay, so here's an informal definition of the pumping lemma. Suppose you have a language that's regular. Since you have a language that's regular, for sure there's a DFA for that language. And what you do is you pretend you know exactly how many states are in that DFA. We're just always going to call that number M, okay? And any string in the language, this is what the pumping lemma says, if you have a regular language, then any string in the language that's at least M characters long can be pumped to make more strings in the language. And all of those strings that you get from pumping are going to be in the language. So this is going to be our hack. What we're going to do is if we have a DFA which has M states in it, and we can find just one string in its language that's at least M characters long that can't be pumped, then the pumping lemma, since it says if it's regular, there's always strings that are that can be pumped, right? If their length is long enough. The pumping lemma is going to tell us that if we can find the one string that cannot be pumped, then the language is not regular. So that's kind of the informal idea behind the pumping lemma. And so how are we going to, or behind proofs that use the pumping lemma? And here's how we're going to write a proof that uses the pumping lemma to to prove that a language is not regular. All right, we're going to use proof by contradiction, which is super cool, right? Because we're going to assume that our language is regular and just say, oh yeah, the language is regular. You're saying the language is regular. That's great. The language is regular. And then we're going to say, well, if a language is regular, then the pumping lemma gives us, then the pumping lemma tells us that we can pick any string in L whose length is greater than or equal to M. Oh, what's M? M is the number of states in the DFA. And we're going to show that you can't pump that string, okay? You can't keep adding these Y parts to it. So what happened? We said L is regular, right? And so we just have to pick one string and show it can't be pumped. And then all of a sudden we're stuck because since it's regular, any string is pumpable. But wait, we said our string isn't pumpable, but it is, but it should be, but it isn't, but it should be, but it isn't. So we have a contradiction. And remember, with proof by contradiction, when you get to a contradiction, you have to, you say, oh, therefore my assumption is false. What was my assumption? L is a regular language. So I guess my language must not be regular. So this is kind of the outline of what we're going to do. Let's look at it much more closely, okay? So here's the formal definition of the pumping lemma for regular languages that you'll find in the book. It's a little bit more complicated than what we've been talking about, but I think you'll get it given what we've been talking about. All right? So L is an infinite regular language over the alphabet A. And if L is an infinite regular language over the alphabet A, then there's some number, M. Pumping lemma doesn't say, oh, M is going to be that number of states in the DFA, but trust me, M's the number of states in that DFA. Such that for any string S, where S is in my language, and it's also the case that the length of S is at least as long as M, right? And we need to be at least as long as M. Why? Well, you know why, because we need to have some double. Well, if we have that, then we can split into X, Y, and Z, right? X, Y, and Z have to be strings that are in my alphabet, right? We're being very general here. Y isn't empty. And S is concatenating X, Y, and Z together. The length of X, Y squished together has to be less than or equal to M. And whatever K I pick, X, Y to the KZ is in L. Okay, so this is the formal definition of the pumping lemma for regular languages. Let's see how we use it. Okay, all our proofs using the pumping lemma are going to be using proof by contradiction. We talked about in the very first week of class, but just to remind you, how do we do proof by contradiction? We assume we've got some fact F. It's true. We do a bunch of smart things that lead you to a contradiction, right? And we draw it like this. Remember, it looks kind of like 4 arrowheads hitting together. Like, after we do all our great stuff, we discovered that the moon is made of green cheese. But the moon is not made of green cheese. But it has to be. But it's not. But it has to be. Well, the only way we could decide that the moon is made of green cheese is if something we did earlier in our proof is wrong. And the thing that we did earlier in our proof that was wrong was our assumption, so therefore F must be false. Okay, that's the outline of a proof by contradiction. Please, 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 if you don't remember more about them, go back and look at the first set of slides. Let me start by just giving you an outline of a pumping lemma proof. We're not going to do it perfectly yet. I'm just giving you an outline. Okay. Let L be a language, right? In this case, I want to prove that the language A to the N, B to the N, where N is any natural number, is not regular. So what strings are in my language? Well, it has lambda, it has AB, it has AA, BB, it has triple A, triple B, and so on, right? So let's let L equal this language, and now we're going to make the key assumption that's going to help us with our proof by contradiction. All right, we're going to assume L is regular. Okay, so if L is regular, then we can make a DFA to recognize it. So there's some number M. We don't know what it is, but there's some number, right? It's just going to be however many states in our DFA. But there's some number M for which the pumping lemma applies. Okay? In particular, any string that's in my language that's at least M characters long, we could split up into our X, Y, Z. Y is not the empty string, right? Y doesn't equal lambda, and these things are true. So, if this is the case, the pumping lemma tells us this is true for every single string in lambda. Sorry, in L. Every single string in my language. If we can find just one example that it's not true for, we've got a contradiction, and therefore our assumption must be false. L must not be regular. Okay? So let's do the real proof now. Okay? And we're just going to go through it step by step. So we start, let L equal our language, and assume that L is regular. There's our assumption. Well, let's also assume that M is the number from the pumping lemma. And now we get to pick any string we want. Any string we want, right? As long as it has at least M characters in it. The string I'm going to pick, and I'm picking it because I know it works for this. We'll talk later about how to pick a good string, but I'm picking this one because I know it works. All right? And I'm going to pick the string A to the M, B to the M. So, just review. Let's suppose that the DFA that recognizes this language, right? I'm pretending there is one. Let's pretend that the DFA that recognizes this language has 5 states in it. Then I would be picking S to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Right? Oh, but maybe it doesn't have 5 states in it. Right? Maybe it has 7 states in it. Well, that means that M is 7. So my string is going to be A to the 7, B to the 7, which is 1, 2, 3, 4, 5, 6, 7 A's, and then 1, 2, 3, 4, 5, 6, how many do I have? 1, 2, 3, 4, 5, 6, 7 B's, right? So in that case, this is what S would be, right? I don't actually know what M is. Well, actually I know M doesn't exist, right? Because L's not regular. But let's pretend it does for a minute. Maybe, you know, for all we know, M is 753. So that means my string is A to the 753, B to the 753. So there are 753 A's in a row followed by 753 B's in a row. Okay? But whatever's the case, no matter what is the case, we're just going to let S equal A to the M, B to the M, whatever the M is. Okay? Now, whatever I picked for my S, A to the M, B to the M, that's certainly in my language, right? Because here's what my language is, and A to the M, B to the M is in this language, so that's a check. And the length of S is greater than or equal to M. Well, sure it is. How long is S? It turns S has 2 times M letters in it, right? Because it has M A's, right? A, and there are M of these, and then B, however many. So how many letters total? There are 2 times M. So if there's 2 times M, well, I know that 2 times M is greater than or equal to M, so that's true. So the pumping lemma applies. Now, by the pumping lemma, we can split our string into an XYZ part, where we know for sure Y isn't lambda, and we know that if I squish the X and Y part together, the number of letters in that is less than or equal to M. Okay? Given that the XY part is less than or equal to M, that means the XY part must just have A's, right? Because remember, I had a bunch of A's, right? Followed by a bunch of B's, right? And there's M of these and M of these. So if the number of letters in XY is at most M, then the biggest XY could be is all these A's. right? So XY has to just have A's in it. Now, you can say, boy, that's lucky, or you can say, boy, Dr. K picked a good string. Okay, so we know that XY is just A's. But if the X part is all A's and the Y part is all A's, Y has to have at least one A, maybe more, because we know Y is not lambda, Y is not the empty string. So let's just say, I don't know, Y has K A's in it. I don't know what K is, but, you know, Y has either 1 A or 2 A's or 5 A's. K is however many that is. So Y, you know, if K is 3, Y is AAA. And if K is 5, Y is 5 A's, and so on. Okay. We know by the pumping lemma that XYYZ has to be in L, right? That's just the rule. We take our X, we put 2 copies of the Y, we put Z, whatever those pieces were, that's in my language. Okay. Let's just pause for 1 second and let's think about what XYYZ is in this case. Okay, in order to figure out what XYYZ is, we need to think a little bit about what the X part, the Y part, and the Z part are, right? So we can figure it out. And so let's just go back to what we know. We know that S is this string A to the M, B to the M, and that the X, Y, and Z parts are, you know, the X, Y, and Z parts concatenated together give us S. And we also know that Y is not empty, Y is not equal to lambda, and also the length of the XY part is less than or equal to M. And we said, let's just assume that Y has, well, we said we know, for sure we know, because the length of the XY part is less than or equal to M, we know the XY part happens in the first M letters of my string, and the first M letters of my string are all A's, right? So we absolutely know that Y is some number of A's. The only thing we don't know is how many of them, right? We called it K. And we know that K is a natural number, right? And we also know K is not 0, right? K has to be greater than 0 because we know Y is not empty, right? Y isn't the empty string, so K has to be greater than 0. We also know that the biggest K could possibly be, and this is only if X actually is lambda, it would be M, right? So K could be M A's in a row if if Y got all of the A's, right? Then K would be M, because remember, K is the number of A's, right? I said Y is A to the K, okay? What about X? Well, I guess we need another variable for that. I'm going to call it Q. Let's suppose there are Q A's in my string, right? Because remember, if we just look at my string for a minute, let's see if I can do this. My string is going to be a whole bunch of A's, right? A, and then a whole bunch of B's, B, right? But we know that the X and Y part are in here, right? So the Y could, in fact, be all of the A's. And if the Y is all of the A's, then the X comes before that. It's just the empty string. But maybe the Y starts here, and so the X is 2 A's. Or maybe the Y starts in here, and so the X is 4 A's or something, right? So X is going to be some number of A's where we'll call it Q. But we know more than just Q as a natural number, right? We know that Q can't be smaller than 0, right? The smallest Q can be a 0. And the biggest Q could be is if we take, if we say, oh, well, maybe Y goes all the way up to the end, the Y part, right? Then the most A's that X could get is whatever's in the beginning part here, right? So there's M A's here, and if we take away the K of them that are in Y, the most we could have left over is M minus K left over for that X part, right? So, for example, if K is 1 and this whole M was 10, then maybe it's possible that Y is just this 1A, and so then 10 minus 1 is 9. If Y is just this A, then X is everything up to the beginning of Y, right? No matter what, X is everything up to the beginning of Y. Of course, it's possible if there are 10 A's here, then Y is just a single A, that maybe Y is this A, and so that would make X everything up to that A, which would just be these two, and the z would be the rest of it, right? But I'm trying to figure out what is the biggest number that this q could be, right? What's the most a's that could be part of x? And the most a's that could be part of x is whatever's left over after I use sum up for the y part, right? After I use how many up? After I use k up. So that's where I get this 0 is less than or equal to q is less than or equal to m minus k. And what's z? Well, z is everything left over. What's everything left over? Well, it's any a's that are left over. So take all the a's, which is m, get rid of k of them for all the ones that are used up by the y, get rid of q of them for all the ones that are left, used up for the x, right? And then all of the b's, because for sure the b's are not in z, right? And now this is all in terms of the variables we already have, right? We don't have any new variables here, so I don't have to tell you anything else about these guys. Whereas with k, I needed to tell you what's the range of k. With q, I need to tell you what's the range of q. Here, I'm using variables I've already talked about before. All right, and now we can figure out what we were trying to do in the first place, which is what is x, y, y, z, right? And how do I figure out x, y, y, z? Well, I just copy x. X is the a to the q part, right? So x is this piece here, right? And what's y? Well, y is a to the k, so y is this little piece. And then another y, because I want x, y, y, z, so there's another piece. And what's z? I just copy this whole thing, so I've got that whole thing, right? So what we end up with is that x, y, y, z equals this expression, right? But remember that this means QA's in a row, and then KA's in a row, and then another KA's in a row, and then M minus K minus QA's in a row. And if I have QA's in a row followed by KA's in a row, I could just add them together, right? So I add all those exponents together, right? Or subtract the ones that I'm subtracting off. And when I say, what's Q plus K plus M minus K minus Q, well, I got a Q minus Q, so those cancel out. And I have a K minus K, so those cancel out. So I end up with K plus M, right? Or as I wrote here, A to the M plus K, right? So when I am, so what's my X, Y, Y, Z? If I pick this string, A to the M, B to the M, right? Then because of the rules that I had to conclude this was what my Y was, this is what my X was, and this is what my Z was. And so my X, Y, Y, Z string ends up being A to the M plus K, B to the M. So now let's go back to the rest of the proof. All right, so we're back to our proof, right? We left off here, right? We're trying to figure out what X, Y, Y, Z was, but now we know. So let's pretend that we pasted all our math we did in here. We don't have enough space. But X, Y, Y, Z is this, right? And we know that K is greater than 0. We know that, right? Because we saw it in our math. Go back and look. But hang on. Here's what X, Y, Y, Z is, right? X, Y, Y, Z is a string that has a bunch of A's, followed by a bunch of B's. But how many A's? Well, first there's K of them, and then there's another M, but there's only M B's. But my language says I have to have the same number. But my string doesn't have the same number. So my string is not in this language. But wait, the pumping lemma tells me my string has to be in this language. But wait, my string's not in the language. But the pumping lemma tells me it has to be, but it's not. We have a contradiction. So notice I drew, oops, sorry. I drew the nice contradiction symbol. So our assumption must be false. What was our assumption? We assumed L was regular. We were wrong. Thus, L isn't regular, QED. We're done. So in this week's module, you'll find a document that's called something like plug and chug outline of a proof that a language is not regular using the pumping lemma. And I've compressed it a little bit here, but this is what it looks like. And what I want you to do is pause the video now, print out this thing if you don't have it, and just take a look and say, yeah, I kind of get it. I see how the proof we just did fits this outline, right? Because an awful lot of what you can do for these proofs is just write statement I want to prove, colon, fill in language is not a regular language. Here's my proof. And if you do it following my outline, you're going to put together a decent proof that's going to get you some reasonable credit, even if you're missing some stuff. So make sure you print out that outline and compare the proof of our proof that A to the N, B to the N is not a regular language and how that matches that outline that I showed you. So just to review before we do some more examples, for the pumping lemma, the pumping lemma says if you have a regular language, then there's a DFA for that language. We knew that already, right? And you just pretend you know exactly how many states are in that language, and we're just going to call it M. And then every string in that language that's at least M characters long can be pumped to make more strings in the language. And remember, the key is if we can find just one string that is at least M characters long that cannot be pumped, then we get our contradiction, right? And the hard thing about doing this is we got to figure out how do we pick a good string to use, right? So here's the outline again, right? This thing I keep calling the plug and chug outline. And we want to pick a good string to use so that when we say let S equal, and we just need to let S equal any old string that is at least M characters long that is also in my language, right? So then we can say this next line, since S is in my language and the length of S is greater than or equal to M, the pumping lemma must apply, right? So we need to make sure that it is at least M characters long. Keeping in mind we don't know what M is. We don't have the DFA. We don't know if M is 10 or if M is 12 or if M is 15. So what we're going to have to do is we are going to have to pick a string that has M characters in it somewhere, so we know we're at least M no matter what M is. Right? So let's talk about how you pick that good string, right? In the previous proof, right, for A to the N, B to the N, we picked S was A to the M, B to the M, right? I didn't pick this by random, and I didn't just replace all the N's in here with M's. Often that actually works, but I thought about it and I said, okay, well, for starters, this string is definitely M characters long. In fact, it's 2 times M characters long, right? Because there's MAs and MBs, right? And the other thing that I did is I'm trying to make it so when I pump it, my string is not in my language anymore, right? So I said, let me make the first M letters here be A. Because if I make the first M letters A, then when I pump it, I know everything in my string that I'm going to be pumping, the Y part, is just going to be A's. And since I'm supposed to have the same number of A's as B's, and I add more A's, it's not going to work, right? And I really thought about what's the sort of simplest thing I can pick that when I pump it is going to mess up. And just as a side, I could have picked A to the M times 2, B to the M times 2, right? So 2 MAs followed by 2 MBs. Y, right? What's the Y part? Because the Y part has to happen in the first M letters, the Y part would still be all A's. So this would be a perfectly fine string, right? It's in the language because it has the same number of A's and B's. And yet when I try to pump something where I'm just adding A's, I end up with something that doesn't have the same number of B's as A's. So let's see, what would have happened if we said that instead of our string being A to the M, B to the M, our string was A to the 2M, right, or M times 2, B to the 2M. So now we have, you know, if M is 10, then we have 20 A's and 20 B's. But if M was 12, we'd have 24 A's and 24 B's. We don't know what M is. But we do know still that my string is going to look something like this. A bunch of A's, right? And then a bunch of B's, right? Where it's the same number of A's and B's, right? And we happen to know that there are 2 times M A's here, right? All of that is 2 times MA's, right? But we know still from the pumping lemma that the length of xy is less than or equal to m, right? So the xy part of our string has to happen in whatever the first m, that doesn't say first, does it? But for the first m characters in this string, right? And the first m characters are in the string. Well, if the first two m characters are in the string are all a's, then no matter what m is, the first m ones are a's, right? So we're back to something similar to what we had before. We're going to have y is going to have to equal a to some value. Let's call it a to the k. But what we need to do, let's make a little bit more room here. What we need to do is we say, okay, well, y is a to the k, and I know that my k has to be greater than 0. It can't be empty because y can't be the empty string by the pumping lemma. And the longest y could be just from the same argument as before. Longest y could be is m. And x, well, you know what? We have exactly the same thing again. X is whatever a's come before the y part, right? So x is going to be a to something. You know, maybe I'll make it, I don't remember what I did before. Let's make it p, right? It could be any old letter, right? I'm just saying there's p a's in a row. And that's what my x is. Where this p part could actually be equal to 0. And it definitely has to be less than or equal to, let's see, now, m, yeah, it's just m minus k again, right? Because I don't know how many a's we used up with y. We could have used as many as m of them, in which case p would be the empty string. Or maybe we only used like one of them, in which case the x part, sorry, p is not the empty string. P is 0. And x would be the empty string. Or we could have, you know, maybe we only used up 2 a's in the y part, and if it was the last two characters in the first m, then the x one could be all of those, right? We have no idea what x is. We just know that x is either lambda or some a's, and we know that y is either, well, no, y can't be lambda, right? We know y is at least one a, maybe a bunch of them. And it's useful to be able to say, okay, well, y can't be more than m of them, m a's, and it has to be more than 0. Whereas the p part, well, it could actually equal 0, and it has to be less than or equal to m minus k. And then let's just finish this off and say, well, what's the z part? Well, z is really everything we haven't used so far, right? So z is going to start with some a's, definitely, because we have 2m of them. So z is going to be how many a's? Well, it's all the a's minus any we used for the x part. So we take away p of them from using them from the x part, right? And then we take away another k of them that we used from the y part. And then we have our b's, which is just b to the 2m, right? So this string that we started with, right, a to the m times 2, b to the m times 2, definitely in our language. And, you know, we figured out our x, y, z, and we can, you know, if we were working on the pumping lemma proof, let me shrink this a bit more. Come on. We could say, well, let's figure out what x, y, y, z is, because that's supposed to be in our language. Ooh, that's hideous. I used the highlighter instead of the pencil. Sorry. Here's the pencil. So what is x? That looks a bit better, right? X, y, y, z equal? Well, x is a to the p, and y is a to the k, and then another y is another a to the k, and then our z is an a to the 2m minus p minus k, followed by b to the 2m, and let's do the math. We have a p plus k. Let's see, we've got p, oh, and there's a minus, right? These are all a's, right? So we got a p and a minus p and a k and a minus k. So I think what we're going to get is x, y, y, z equals a, well, that a to the p and the minus p and the k and minus k. So we end up with a to the k plus 2m times b to the 2m. And of course we know that that k is greater than 0, right, because of our equation up here. So we'd find another contradiction for the pumping lemma. Interestingly enough, if we wanted to, we could also compute xz and say, you know what, xz is also not in the language, right? What would xz be? Well, just looking at what we've got, xz is going to be a to the p, and then followed by z is a to the 2m minus p minus k, b to the 2m. And if we do the math on that, that equals, what do we got? We have a to the p plus 2m minus p minus k, b to the 2m, and we have a plus p minus p. So we get that xz equals a to the 2m minus k, b to the 2m. But again, look at that. That k is positive, so this string isn't in our language because now we have fewer a's than b's, right? So whichever way we did this, it would work. So let's consider this language. Let's show that this language, the set of all palindromes over the alphabet A, B of odd length, are not regular, okay? So I want to prove that the language L, all palindromes over the language, so the language L equals this is not regular, okay? I want to prove this, and I get to pick one string, right? And I'm trying to think, well, first off, what's a palindrome, right? So just to review, palindrome is a string where it looks the same if you start at the front or the back. So if I do like A, B, A, that's a palindrome, or A, B, B, A, B, B, A, that's another palindrome, right? Because if I read it this way or this way, it's the same. AA is a palindrome, though that's a palindrome of even length, right? So we're talking about palindromes of odd length, okay? And what I need to do is I need to say, well, it has to be at least m characters long, right? So my first criteria is I need to make sure it's at least m characters long. And I also want to pick a string that, you know, pumping will mess it up, right? So the question is, how do I do this? And my first thought is with every single string that I try to do on the pumping lemma, my first thought is, can I start with something like a to the m? Because that is definitely m letters long, right? Now I don't know if a to the m is odd or even, right, of odd or even length. So I could say, you know, a to the m, a to the m, well, that's definitely of odd length, right? But if I add more a's to this, it's still going to be a palindrome, so that doesn't really help me much. So I guess I need something that's going to mess up, right? And it may not be obvious. It may take a little time. You have to see a few examples of this to get it. But, you know, what about a to the m, b a to the m? Well, that is definitely in my language, right? That's a palindrome over AB of odd length. And the interesting thing here is because I have the a to the m at the beginning, I know for sure that y is going to be all a's. Right? So what's going to happen if I have x, y, y, z? Well, if I have x, y, y, z, and y is all a's, so now I say, you know, let's suppose y is a to the k for some k, and I know for a fact that k is greater than or equal to 1, and it is less than or equal to m, right? But so that means that x, y, y, z, right? If I do the math through, what I find is that x, y, y, z is equal to a to the m plus k, b a to the m, and I say, wait, that's not in my language, right? In terms of doing the proof, so now I've done my scratch work, right? In terms of doing the proof, I have to go and do the whole thing again. So let me go and get that outline, and we'll do it on the outline. All right, so here is how we're going to prove this, okay? Here's a statement I want to prove, so let's cross out this fill in the blank, and we're going to write the thing that I want to prove is that the set of all palindromes over the alphabet A, B, I should say all odd palindromes over the alphabet A, B, is not a regular language. Proof. Well, let L equal the set of all odd palindromes over the alphabet A, B. Assume L is regular. Let M be the number from the pumping lemma. Let S equal, and we're going to put in up here, we're going to put A to the M, B, A to the M. Since S is in my language, yes it is, right? Because that's a palindrome of odd length. And the length of S is greater than or equal to M because the length of S actually equals 2M plus 1, right? The pumping lemma must apply. Specifically, S can be split up into x, y, z, where y is not lambda and the nth of xy is less than m. And now I get to say y must be all a's and so y takes the form a to the k, where k is greater than or equal to 1 and less than or equal to m, right? By the pumping lemma, x, y, y, z is in the language. So what is x, y, y, z? Well, let's see. Our string S was a to the m, b, a to the m. So our y part, well, our y part, remember the first m letters are all a's again. See a pattern here? So our y part is going to be a to the k, where, well, k has to be, k has to be greater than 0, right? Because the y part can't be lambda, and the length at most is m. And our x part, well, that's going to be a bunch of a's too, because that's what ever comes before the y part. So let's get super radical. Let's say x equals a to the w, right? It has w a's instead of k. Well, what do we know about w? Well, W could actually equal 0, and it's going to be less than or equal to M minus K. And Z is everything else. So Z is going to be all the remaining A's. So Z is going to be A to the M minus all the ones from X minus all the ones from Y, and then a single B, and then the A's at the M. Sorry, the A's at the end. So X, Y, Y, Z is, let's put this together. X is A to the W, Y is A to the K, and another A to the K, and then our Z part, which I never seem to leave room for. So that's our A to the M minus W minus K. Still didn't leave enough room. B to the, oh sorry, just one B, right? And then A to the M. And so if we do the math, we have A to the W plus K plus M minus W minus K, B, A to the M. And let's see, we have a W minus W and a K minus K. So we get that equals A to the K plus M, and then our B, and then an A to the M. And let's just finish out our proof on this page. So we have X, Y, Y, Z equals this thing. Oh, but wait a minute. That means that X, Y, Y, Z is not in our language, right? Because our language was palindromes, and now we have more A's on the left side of that B than the right side, odd palindromes, right? And so it's not, our X, Y, Y, Z isn't in the language, but by the pumping lemma, it should be in the language, but it's not in the language, but by the pumping lemma, it should be in the language. Therefore, we have a contradiction. Woohoo, right? So thus, our assumption must not be true. What was our assumption? Our assumption was that L was regular, so we can say thus L is not regular. QED. Now I know that these proofs get a little bit yucky. It's hard to look at these. So what I'm going to do is I'm going to also upload to the class website some just typed out versions of these proofs and variations on them so you can take a look. Now that we've seen a couple of pumping lemma proofs in great detail, what I want to do is just talk to you about a few more examples, and I'm going to skip most of the proof outline and just talk to you about how do I pick a string, and once I've picked that string, what's the XYYZ or the XZ kind of string that I can show is not in the language. Okay, so the first one that we're going to do is, we've already done odd palindromes, right? What if I say I just want to do where my language is all palindromes? Ooh, I picked that highlighter thing again. Okay. What if I want my language to just be the set of all palindromes, right? Well, think about this for 1 second. If I want my language to be the set of all palindromes, and I can pick any old string I want, right? As long as I pick a string that's in my language. Oh, sorry, all palindromes, let's say over the alphabet A, B, right? I can pick any old string in my language. So why don't I pick, oh, here's one, A to the N, B, A to the N. Is that a palindrome over the alphabet AB? It sure is. Can I just use the entire rest of the previous proof that I had? You bet. Okay, that was easy. All right, let's try another one that seems a little bit harder. Let's do one that is a, what about even palindromes, right? What about if our language equals the set of all even palindromes over the alphabet AB? Well, even palindromes makes it a little bit harder, right? We have to have an even number of letters in our string. And, you know, that when we were doing odds, it was great because we had a bunch of A's with just one B in the middle. We knew it was odd because we had the same number of A's on both sides. But now we're doing evens, so it feels a little bit different because, like, if I do, well, I can't just do A to the M, right, with nothing in the middle, because then if I add more A's, it may still be it may still be in my language. So that's kind of weird. And I can't do what we did before, which is A to the M, B, A to the M, because that's odd length, right? Because we have, you know, this has 2M plus 1 letters in my string, right? But what about this one? We could do A to the M, and then 2 B's, and then A to the M. I would say this string here is, well, it's of even length, right? Because how many characters are in it? Well, we have 2M plus 2 characters in it, so it's of even length, and it's a palindrome, so it looks good to me, right? And when we're trying to figure out what is Y, well, look, Y is still going to just be a bunch of A's, right? So Y is going to be, you know, A to the K, such that K is greater than 0, less than or equal to M. And the X is going to be a bunch of A's also, so we have A to the, I don't know what letter to use. We'll use P again, where P could be 0 letters, right? Because X could be lambda. And we've used up K of those letters from the first M letters, so we can't have it quite as big. And Z is everything else. So what's everything else? Everything else is any A's that remain. So that would be A to the M. Oh, sorry, we're doing Z is the leftover one. So A to the M minus the K we used up, minus the P we used up. And then the rest of the string, B, B, A to the M. And so if you're doing your proof to show that even palindromes are not regular, the hard part's done now, right? Because we figured out what X, Y, and Z are. So if you just take this, you know, pause the video, take this and say, what's XZ? XZ should be in the language, but if you figure out what XZ is using this stuff over here, you'll find that XZ isn't in the language. Or you could choose to do it XYYZ, because XYYZ also isn't in the language. So here's an interesting one. What about this one? Here's the language A to the N, B to the K. So we have potentially different numbers of A's and B's. And what I say is we always have, N is always greater than or equal to K. So we always have at least as many A's as B's, maybe more A's than B's, right? So this is kind of interesting, right? Because if you think about it for a minute, the trick we've used so far for most things isn't going to work for us, because if we start with the string, let's suppose we let our S equal A to the M. Well, if we let it be A to the M, B to the M, that's in my language, right? and the number of A's is indeed greater than or equal to the number of B's. But when I pump this, when you look at what the X, Y, and Z are going to be, you'll find that we get the same kind of X and Y again, right, made up of all A's. And if we were to compute X, Y, Y, Z, well, let's see. Y is going to be our old friend. Well, I guess we can't do a to the K because we've already used up K. So we'll just do a to the C, where C is greater than 0 and less than or equal to M, right? And X is going to be a to the something else, maybe P, where 0 is less than or equal to P is less than or equal to M minus C, right? And Z is going to be everything else. So Z is going to be a to the M minus C minus P. That's not doing very well. Followed by, so that's all leftover A's, followed by B to the M. So if we look at X, Y, Y, Z in this case, what we get is that X, Y, Y, Z equals, well, X is a to the P, and Y is a to the C, and then another a to the C, and then Z is a to the M minus C minus P, that's a P, B to the M. And so when we figure that out, right, we have a C, and the C cancels out, and we have a P, and the P cancels out, and we end up with X, Y, Y, Z equals A to the C plus M, B to the M, right? But remember, the thing we were trying to show is not regular is these strings where the number of A's is greater than or equal to the number of B's, right? And let me squidge this. What we got here is we have the number of A's greater than the number of B's, so that's not a problem, right? So we couldn't use X, Y, Y, Z to complete this proof. It just wouldn't work. The good news is that what we could do instead, so let's see, let's get rid of all of this X, Y, Y, Z stuff, because that didn't help us. But we can still use what we know about X, Y, and Z. What if we just try and take a look at XZ, right? Because XZ is also supposed to be in the language. And what's XZ? Well, XZ, X is A to the P, and the Z part is A to the M minus C minus P, and then a B to the M. So XZ equals that, which equals, we got the P minus P, so we have A to the M minus C, B to the M. And XZ should be in our language, but hang on a minute, our language has more A's than B's, and we know for a fact that C has to be strictly greater than 0, right? We wrote it down there. So we have fewer A's than B's, so we're good. You know, we have a contradiction again. And again, what do we need to do these proofs? We need to pick one string and show that when we pump that string, it's not in the language anymore. And pumping the string can be adding Y's or it can be taking Y away. All of those are fine. Okay, we're going to do one last problem, or at least piece of a problem, right? I'm not going to show you the full proof again because I figure you have my outline. What you really need to know is the middle part of the proof where we pick a string and try and figure out what's going on. So this is an interesting language. It starts with one A, and then we've got the same number of B's and A's after that, right? So this is different than what we've been doing before, because if I pick a string and if I use our standard technique of let's try just substituting the m for the n's and see if that string works for us. So we say let's choose s equals a, b to the m, a to the m, right? All of a sudden, we're in an uncomfortable situation for us, because when we say, let's figure out what x, y, z is, right? Y doesn't have to be all a's anymore, right? Let's see, what could y be? Y could be just an a, or y could be an a and some b's, or y could be just some b's, right? You see where I'm coming from here? Because let's just move over for a second. Oops, sorry, that didn't work very well. You know, let's just pretend for a minute. It's not the case, but let's just pretend for a minute that we happen to know that m was 4, right? Then our language would be an A, and 1, 2, 3, 4 B's, and 1, 2, 3, 4 A's, right? And we just do not know how the split's going to happen. Remember that whole split thing at the beginning of the video, or of the previous video that we did, that was, you know, so good, where we we said, oh, here we go, we're splitting it like this, so this is y. Oh no, you know what, that split wasn't the split that was going to happen. We were actually going to split it like this, so x is lambda and y is this piece and the whole rest of it is z, right? We have no idea how this thing is going to split, and everything we've done so far has always said, oh, but you know, life is good because our y has to be all a's, because the first however many letters are all a's, but the first m letters, right? But in this thing, we know we have exactly one a at the beginning, and then we have this b to the m, a to the n thing, a to the m thing. So the only way we can do this is to say, okay, well, y could be a couple of different things, right? In fact, y could kind of be 3 different things, right? So y could just equal a, right? And y could just equal some b's. Maybe it's b to the k, right? So one option is y is just a. One option is that, let's just cross this out. One option is that y is a bunch of b's, where I guess k is greater than 0 and less than or equal to, well, this is interesting. We have to say m minus 1. You with me? It's got to be m minus 1, because the first m letters are, a is 1 letter, and then we have m minus 1 b's, right? Or the last possibility is y is an a followed by some b's, right? So maybe y is an a, and then we have kb's, right? Where 0 is less than, or oops, sorry, 0 is less than k, because we have to have at least one thing for my y, is less than or equal to m minus 1, right? So we have 3 cases here, right? Y could just be an a. Y could be just a bunch of b's, 1 or more b's. Or y could be an a and then a few b's, right? And if I just say, oh, well, let's assume y is a, and I do my whole proof and I figure it out, and I say, look, x, y, y, z isn't in the language. Well, that's all very well and good, but remember that I can only get a contradiction if I show no matter what y is, x, y, y, z is still not in the language, right? So for proofs like this, I actually have to do 3 different cases, right? And I say, well, let's see. In case 1, if y equals a, so let's see if I can make this a little bit bigger. So if y equals a, and there's my string there so you can still see it. Well, if y equals a, then x is going to be everything, well, no, x is going to be lambda, right? X is nothing. And z is everything else. So z is going to be b to the m, a to the m, right? And if we look at x, y, y, z, that's going to be a lambda, and then two a's, and then a b to the m, a to the m. And oh, look, x, y, y, z isn't in my language, right? Because we have two a's now instead of one, so that's no good. So we know that if this whole thing were going to work, y wouldn't just be a. But if this is my string, well, maybe y could be just a bunch of b's, right? What happens if y is just a bunch of b's? Well, if y is just a bunch of b's, right, then x is going to be everything before those b's, right? So I guess x is going to definitely have that a at the front, and then it's going to have a bunch of b's, maybe b to the, I'll make it a p, where, let's see, how many b's could we have there? Well, I guess we can have p is going to be greater than or equal to 0. We could have 0 b's, right? Or we could have whatever's left over, which is going to be our m minus 1, the b's that we could possibly reach in the first m letters, minus the k that we've used up, right? And so if that's the case, we've got y, we've got x, we've got, oh, we got to figure out z. Z is going to be everything else. So z is going to be the leftover b's. So z is going to be all mb's minus the k we used up minus the p of them that we used up, and then our a to the m, right? We're going to have more space for that other example in a minute. So let's figure out our x, y, y, z in this case, right? Let's do that. Our x, y, y, z in this case is, well, x is a b to the p, and y is b to the k, and then we throw in another b to the k, and then our z is b to the m minus k minus p, a to the m. And so when we add all those a's up, sorry, all those b's up, we get, let's see, we have a, that was a minus. So we have a p minus p and a k minus k, and we get a, b to the k plus m, a to the m, and that is not in our language, right? So remember what we were doing again. We said we have three cases. If this is our string, it's possible that y is just a's. Oh no, look, we said it couldn't be just an a. Sorry, y is just an a. Or okay, it's possible that y is just b's, but then we did this and we said, nope, y can't just be b's. So, you know, if this string is pumpable, it's going to have to be the case that y is actually an a and then some b's, right? So let's just look at this example for a minute. And I'm going to sort of do this work over in this corner here, okay? So if y is a b to the k, where k is k is greater than 0 and less than or equal to m minus 1, then the x is going to have to be lambda, right? Because we only have one a and y's already taken it. And the z is going to be all the rest of the b's. So z is going to be b to the m minus k, and then all of the a to the m's. And we could figure out what x, y, y, z is here too, and show that if we pump to get x, y, y, z, it's not in the language. But you know what? Because I'm feeling a little bit short on space, I'm going to just try xz. So what is xz? Xz is, well, a lambda, right? Followed by b to the m minus k, a to the m. And boy, xz isn't in my language, right? For sure it's not in my language. So now let's go back and let's see what we've done here, okay? And what I really want you to do after this is take a look. I'm going to upload a full version of this proof onto the class website. But for now, let's just look. We said, let's pick this string, which is in our language, right? A, B to the M, A to the M. We said if we pick that string, one of these things has to be true, one of these three. Either Y is just an A, or Y is just a bunch of B's, or Y is an A and a bunch of B's. But then we said, well, this part isn't possible because we can't pump it. And this part isn't possible because we can't pump it. And this part isn't possible, so we can't pump it. So now we have our contradiction, because in order for this to be, in order for this to be a regular language, this string has to be pumpable somehow. And no matter how we pick the Y, it's not pumpable. So therefore, we can say the language isn't regular, and we just had to use a little bit more work to do it. So I am going to make this, turn this into a nicer PDF, and I will upload that to the website too. So to wrap up, the key for this whole lecture is really to be able to pick some interesting strings, right? Make sure that your string is at least M characters long, and then look at what happens when you pump that string. What's the X part? What's the Y part? What's the Z part? How do you split them up? And that will help you figure out, help you prove it's not regular.